Hello viewers, I am Dr. Mala Das Sharma, retired professor of St. Pius X Degree and PG College for Women, Hyderabad. Welcome to my channel Chemphilic. Let's start 46th episode of Teaching Chemistry through Riddle. Here is our riddle number 46, which goes like this. Compound X has two same functional groups at two different positions. It is represented as resonance hybrid structures. It can be added up with two molecules of ozone. The resultant adduct on hydrolysis produces one molecule of the simplest dialdehyde and two molecules of an aliphatic carbonyl compound whose 40% aqueous solution is used as industrial disinfectant as well as preservative. The addition reaction of X with 1 mole of hydrogen halide produces two different products. One predominates at low temperature while the other at high temperature. So this is riddle number 46. Now let's solve this riddle and let's see the questions associated with the riddles. The primary question is, what is compound X? The answer is 1,3-butadiene. CH2 double bond CH, single bond CH, double bond CH2. Second question, what are the resonating structures of X? The answer is 1,3-butadiene is the resonance hybrid of two structures. See here, this is 1,3-butadiene. These two double bonds are separated by single bond. That means conjugation is present. So resonance will occur. So this double bond shifted here and this pi bond will shift to this carbon atom and then we will get the ionic resonance structure. So 1,3-butadiene is the resonance hybrid of these two structures. This is non-polar structure. This is polar structure. Now third question. What are the ozonolysis products of 1,3-butadiene? 1,3-butadiene, there are two double bonds. We know that ozone molecule, that means 3 oxygen atoms, can be added up to one double bond and form the ozonide. That means the adduct is known as the ozonide. So here there are two double bonds. So two molecules of ozone will be added up and the ozonide will be like this. So this is the ozonide. Now this ozonide on hydrolysis undergoes cleavage. So here breaking takes place this way and this way. Similarly this way and this way. So from this part what we will get? We will get HCHO, formaldehyde. Again from this part we will get formaldehyde and from this middle part we will get CHO, that is glyoxal. So this hydrolysis produces the products 2 molecules of formaldehyde and 1 molecule of glyoxal, which is the simplest dialdehyde, and this formaldehyde, we know that 40% solution of formaldehyde is formalin, which is used as disinfectant and preservative. Now fourth question, what are the two different addition products of 1,3-butadiene with hydrogen halide? Show the possible mechanism. Now at low temperature, addition of hydrogen halide, say hydrogen bromide to 1,3-butadiene, gives the 1,2 addition product. That means 1,2 addition dominates. Let's see. So this is 1,3-butadiene, and when hydrogen bromide is added up at low temperature, say minus 75 or minus 80 degrees centigrade, then this hydrogen bromide is added up at this 1,2 position according to or by following Markovnikov's rule. So this is the 1,2 product and this is the major product at low temperature. Contribution is 80%. And we'll get a minor product, that is the 1,4 addition product. That means hydrogen is added up at this 1 position and bromine at the 4 position, and its contribution is 20%. Now at higher temperature 1,4 addition dominates. So when the temperature is increased, say 40 degrees centigrade, room temperature or more than room temperature, say here it is more than room temperature, 40 degrees centigrade. In that case, this 1,4 addition products predominates. See, at room temperature, ratio of 1,2 and 1,4 addition is 45:55. But at 40 degrees centigrade, the ratio is, that is 1,4 and 1,2 ratio is 80:20. That means 80% 1,4 product is obtained. Now let's see the mechanism of addition to 1,3-butadiene. See, here the first step or rate determining step is the protonation. That means this pi bond breaks and gets attached with this H plus, and this bromine hydrogen bonded electron pair shifted to bromine. So bromide ion is formed, and here then the carbocation is formed because this pi bond shifted through this carbon atom to produce the stable carbocation. Now in this carbocation, this positive charge and double bond separated by single bond. So conjugation is present, that means resonance participation occurs. So this double bond will shift here, and then this pi bond will shift here. So you will get the positive charge in this 4th position. So this carbocation is the resonance hybrid of this structure and this structure. But this carbocation has major contribution because it is more stable carbocation than this one. Why more stable? Because it is secondary carbocation, and as it is secondary carbocation, it gets stabilized by hydrogen, that is hyperconjugation by how many hydrogen atoms? 1, 2, 3, and here 1, 4. Whereas these carbocations get stabilized by hyperconjugation of only 1 hydrogen. So it is more stable, and major contribution will be a major contribution of the resonating structure towards the resonance hybrid will be the more stable carbocation. Okay, and when this nucleophile, that is the bromide, attacked at the C2 position will get the 1,2 product, and when the bromide attacked at C4 position will get the 1,4 product. And so here is the mechanism. So this carbocation is formed. This is the resonance hybrid structure. These are the 2 resonating structure, and when this bromide is attacking at this secondary carbocation, that means cation positive charge at the second carbon atom, then you will get the 1,2 addition product. When the bromide attacks at the 4th carbon atom, we will get the 1,4 addition product. The 5th question. Why 1,2 addition product of 1,3-butadiene predominates at low temperature? Now see, at low temperature, the product distribution will be related to the relative energies of the 1,2 and 1,4 transition states. What does it mean? See, I told you initially the rate determining step or the first step is the protonation. Okay, so after protonation, this carbocation has formed. Carbocation is the resonance hybrid structure. It is the resonance hybrid of these 2 structures. and this one is, that means the 1,2 carbocation, means carbocation which can lead to the 1,2 product, that will be the more stable, that means less energy. Now it is at low temperature, that means much energy is not available. So the reaction, you will see in this reaction, the transition state for this 1,2 addition, or the reaction, when the reaction proceeds through this stable carbocation, transition state is less energized. Less energized means this activation energy is low. That means difference of the energy of this transition state and this energy of this reactant. Here the reactant is the carbocation. From the carbocation the product is forming. Whereas energy of the transition state of the reaction when it proceeds through this unstable or less stable carbocation, which can lead to the 1,4 product. So here this activation energy is more, as here for this 1,2 addition which proceeds through this more stable carbocation, activation energy is less, and low temperature means much energy is not available. So reaction favorably follows this path. That means this path means the products will form from this more stable or low energy carbocation, which can lead to the 1,2 addition product. Okay. That means this reaction is known as the kinetically controlled reaction, or this is the kinetically controlled addition reaction of 1,3-butadiene. Therefore, what we observe that this kinetically controlled reaction is governed by the stability of the intermediate. Here the intermediate is the carbocation, and moreover at low temperature this reaction is irreversible. As long as the reaction remains irreversible, in that case the reaction will follow this path. That means this reaction occurs through the more stable carbocation, and it is kinetically controlled reaction, and the product will be 1,2 addition product. So 1,2 addition product will predominate at low temperature, and this is referred to as kinetic control. Now, sixth question. At high temperature, which addition product of 1,3-butadiene is the major product and why? See, at high temperature, the reaction becomes reversible, and then what happens? This equilibrium sets up. So this equilibrium between this product and this product is established. Okay. In that case, the reaction will governed by the stability of the product, not by the stability of the intermediate, okay, or not by the energy difference of the transition state and the reactant. Okay. See here 1,4 product compared to 1,2 product, the 1,4 product is more stable, because here this alkene double bonded 2 carbon atoms are more, what we should say that it is more substituted. It has a di-substituted double bond, but here it is less substituted. It is mono-substituted double bond, here di-substituted. So this 1,4 product is more stable, and at high temperature reaction becomes reversible. Then this reaction is governed by the high temperature, it is governed by the stability of the product, not by the stability of the intermediate, or not by the energy difference, that means or energy of the transition state or activation energy. And this is referred as thermodynamic control. Now let's see here. So this is 1,3-butadiene. Okay. Rate determining step is the protonation. Then this carbocation is formed. Okay, so here carbocation is formed, which is indicated by C, and this carbocation is the resonance hybrid of these two structure. This one is lower energy stable, this one is higher energy less stable. Okay, now so from this lower energy carbocation or stable carbocation, this is the energy of the transition state. That means activation energy is this much from here to here. Whereas when the reaction proceeds through this higher energy carbocation, then this is the transition state and the activation energy will be this much higher. But it is at high temperature. High temperature means the energy is available. So when the energy is available, then reaction can proceed through this high energy transition state, and once it proceeds through this high energy transition state, it will give the more stable product, that is 1,4 product, and at high energy the reaction becomes reversible. So it will give the more stable product. Its energy is much lower than that of this energy, that is 1,2 product, and much lower than that of this energy of the reactant. So what happened? At low temperature, forward reaction favors and it hinders the reverse reaction, and we obtain the kinetically controlled product. But at high temperature, reverse reaction becomes energetically accessible because it has more energy. It is at high temperature. So it can reach to this high energy transition state easily. So once it reaches to the high energy transition state, it will form the more stable product. And it is a reversible reaction. So when the more stable product is forming, so reaction will proceed towards this direction. Okay. And therefore the major product will be 1,4 addition product, and an equilibrium is established here, and this is known as the thermodynamically controlled product. So thermodynamically controlled product is governed by the stability of the product, whereas kinetically controlled product is governed by the stability of the intermediate, or you can say that activation energy or difference in the energy, or you can say that the energy of the transition state, where the low energy transition state will lead to the product. That means we will get the 1,2 product where the activation energy is low. So this is the summary of 1,2,1,4 addition. So first step is, initial step is the rate determining step, that is protonation. Then this carbocation is formed. When the bromide ion attacked at these two positions, you will get the kinetically controlled product or 1,2 addition product. Okay, and this alkene is less stable. And when the bromide ion attacked this carbocation, then we'll get the thermodynamically controlled product, and which is more stable alkene. So at low temperature, reaction is irreversible, and the lowest energy transition state will determine the major product. Already I explained, and this is kinetic control. And high temperature, reaction is reversible, and the product distribution will favor the more stable product. Okay, that is the disubstituted alkene here. This is thermodynamically controlled product. So this first one we call kinetic control, second one this is thermodynamic control. So this is about the 1,2 and 1,4 addition of 1,3-butadiene, and also the thermodynamically controlled product versus kinetically controlled product. So we have come to the end of this video. Thank you.